Okay, so let's start. I will quickly tell you how to play with the code called SAMD. And SAMD is shape adaptive mode decomposition. Okay, and that is the reference is here. This is the reference. I think I put this reference in training material, but you can take a look if you want to know more. And as I mentioned before, the overall goal of this synchrosqueezing of all the shape, all the time frequency analysis, well, there's nothing special. I mean, the goals are kind of similar to what we want to do in signal processing. So we have discussed ridge extraction before, and right now it is about decomposition. So in this code, again, we are still working with simulated data. And I think after today, next time we will talk about something real. We will assemble everything we have discussed so far to study real data and see how to use everything. But today, it is still the simulated data. Okay, so in the folder, the SAMD is the main folder, and all the others are the same, like the shape and so on. And this is, again, the library you can use to generate the ARMA11 random process as noise. And this is nothing but, again, fix the random seed so that you can reproduce. You can change this number as you wish. Then this is the sampling rate. This is just the sampling rate used to generate the signal, which is of high frequency and so on. You can maybe ignore whatever you can play with it. You can change it as you wish. Okay, and then we generate non-sinusoidal oscillatory signals, and just following exactly the same steps as before. But this time, we try to generate simpler wave shapes, but not really that simple. Okay, so what you get is this part. This is the face of the first component. So you remember what phase is and the instantaneous frequency is, right? So let me run everything one by one, step by step, so that we're on the same page. Okay. Then this is how we generate things. Okay. This is X1. And so if you remember, this is the first phase. Okay. And if you plot with it, IF1, you see this is the instantaneous frequency. The instantaneous frequency is not fixed. It starts with 1.6 hertz, going up to 2.8 hertz, and reduce to about 2 hertz. So that is what you get. And if you cum sum it, you get the phase. And then you have amplitude modulation. Okay, so this is how the amplitude modulation looks like. You can see it is not fixed. It is also modulated. Okay, I mean, all these are the same as before. There's nothing really new. What is new is the way we generate wave shape function, but this is actually time varying. Time varying wave shape function. I will remind you what is time varying wave shape function in a bit, but this is how we construct it. First, we generate the fundamental component. This the first one. This is the first. This is the fundamental component of the first IMT function. Okay, and then we assume there are 8 harmonics. Okay, so surely this is kind of a simplified version for the general problem, but it is already complicated. since this is the fundamental component or the first harmonic. Okay, so we start only from 2 to 8. And here we generate modification, generate well, disturbance or whatever, how to call it, disturbance or perturbation. Okay, yeah, perturbation of harmonics or phase harmonics. Okay, and this is what we generate, VIQ. This is the perturbation. VIQ is the perturbation. VIQ. If you look at this guy, you will see that this guy is nothing but a function that will slightly deviate the instantaneous frequency. For example, if I randomly plot the last instantaneous frequency, you see the instantaneous frequency is perturbed up to 0.4 Hertz. And each one will have some slight different perturbation. And this is 8, the II's harmonic, where you see that here is a perturbation that I8. Okay, and then I just reduce the amplitude for simplification. Okay, just random reduction. You can change the amplitude, the global strength of each harmonic. This divided by II divided by 2. This means change the magnetic amplitude of the I's harmonic. Okay, very good. And this is the generate the harmonics. Sorry, the amplitude modulation. Modulation. Okay, you can also make it time harmonic dependent in general, but here we just keep it simple. Okay, so this is AA. So in the end, you get XI. So you can take a look at XI in a bit. We will take a look at XI in a bit, but then you generate the second one, which is exactly the same. We also have 8 harmonics, but with different weighting now. And then you generate noise like before, but this time the noise is the first part. The first part is Gaussian. The second part is T distribution, student T2. Okay, so it's a very fat noise, very fat tail noise. Okay, so then up to here. Okay, that we generate a second intrinsic mode type function and the noise. So you see, the signal to noise ratio is minus 0.8 dB, which is quite a strong noise. Now, we can aid them and generate the final noise, signal. And finally, we downsample it to 100 Hertz. And why do we want to do it from 1000 to 100? Well, there's the main purpose is simply, in general, we want to generate more complicated wave shape function. But in this example, we just keep it simple here. So we downsample it to 100, okay? Okay, downsample. Now it's 100 Hertz, everything just downsample by 10. Then finally, we plot the generated signal for visualization. So that is what you get. Okay, what do you see here? What you see is, this is the first component, this is the second component. The first component, if you pay attention, it is oscillatory, but it is not sinusoidal. Second, you may see that, hey, look, in the very beginning, it is the first peak that is larger, right? And then when time changes, the second peak increases its size. And in the end, the second peak dominates. Okay, and you can see that in the beginning, it oscillates slowly, and suddenly it oscillates fast and slow. But this is not as slow as in the beginning. So this is what we discussed before. This is about time-varying wave shape function. So if you remember, in the previous lecture, we had a discussion about time-varying wave-shape function. The main focus, the main purpose, main motivation was to quantify this kind of time-varying photoplethysmography, morphology, behavior. So what we do was first, you may assume there are k oscillatory components. In our current example, the k is 2. That is, we have 2 IMT functions. And before, you have amplitude modulation, you have wave-shape function, but wave-shape function is fixed. And this is the fixed wave-shape function was the example I gave you in the previous lecture about how to apply the shape algorithm for simplification. But now we consider more complicated one. We have phi1, FEI, and FEI is the phase. Okay, and then I say, well, this is too simple. The wave-shape function is fixed. We cannot do too much. Okay, so to quantify the time-varying wave-shape function, what we do is first we apply decomposition, Fourier series decomposition of SI, right? And after decomposition, you see this is CILO, this is alpha ILO, and what I constructed here, if you pay attention, is where is the code? It's here. If you pay attention, you will see that this alpha ILO is actually this one, this random one. This guy is alpha ILO, and there is a divided by square root of I. This guy is CILO. Okay, and if you think about it, all this summation actually quantifies a fixed wave-shape function, but now I add a perturbation. If VIQ is 0, then you can recover this formula, time-varying wave-shape, fixed wave-shape function. And now I do some generalization. The generalization is we now force to slightly perturb 2 pi L VIT plus alpha IL by introducing VIL, which is a new function. And we need to impose some conditions about VIL. That is VIL, VI1, VI2, VI3, they will satisfy some basic conditions that we have discussed before in the lecture. And this VIL, that will be the amplitude modulation of the LO's harmonic, that we also need to impose some conditions. But the basic idea is we combine AI of T times CILO, and we slightly perturb it to generate BILO, and we combine 2 pi LO BI plus BILO, and slightly perturb it to generate 2 pi VILO, so that you can quantify this time-varying wave-shape function. Here, there's a year, there's no year, and so on. Okay, so that is the basic idea and what we want to capture. And that is the simulated signal. The first one, and if you pay attention to the second one, you see the similar behavior. You see that it's a peak and so on. Okay, and then the peak behavior or the oscillatory pattern changes. And this is a summation. This is a summation. Now, if I give you this some signal, what can you do? That would be the question. And this is a noise. As I mentioned, the first half part is Gaussian noise. The second part will be student T2, which is fat tail, and the variance even doesn't exist. In this case, how far you can do, what can you do? Okay, and this is the noisy signal we will analyze. Okay, so that is how you generate a signal. And the only difference compared with before is that now this time, the wave-shape function is time varied. And later on, we will, when we introduce the manifold model to better quantify the dynamics of wave-shape function, you will see that the wave shape function can be much more complicated than what we are discussing right now. But we will need more complicated tools like manifold learning to help us to decompose the dynamics of wave shape function and the dynamics of of instantaneous frequency and so on. Now, this is the second step. Well, after you generate a signal, now the mission is to decompose. Mission is decompose y into x1 and x2. Okay, so I think you can easily believe me that this is a very challenging mission. If you use the traditional signal processing tools, so we need to do something a bit more. Okay, even if you simply use the synchrosqueezing, you can play with it. If you only use synchrosqueezing and try to decompose the harmonics one by one, it is not easy. So the first mission is we want to estimate instantaneous frequency, amplitude modulation using any algorithms you like. Okay, and here we will use the D-shape algorithm. Okay, and how do we do it? Like what we discussed last time, we will set up the parameters, and I will not repeat it, and we run D-shape algorithm, right? And then you have some sampling periods and so on, and blah blah blah. So maybe we can change this to 12 so that you can see better picture. Let's see. Well, maybe 10 is also good, but anyways. Okay, so let's run it here. So this is a picture you get. As we discussed before, this is the short-time Fourier transform of the clean signal. And you see, there are many curves, and it is not easy to see which one is which. But if you run the shape algorithm, you get two components. And if you pay attention, this time, the instantaneous frequency of harmonics are related with perturbation, but still the shape is capable of recover everything. Okay, and there are theoretical support of why this holds, which you can check if you have interest in the theoretical paper. And this is a synchrosqueezing of the D-shape algorithm. Okay, what you do is very simple. Once you get this D-shape short-time Fourier transform, you apply the squeezing rules, reassignment rules, and to squeeze this D-shape short-time Fourier transform to get D-shape sorry, this is D-shape short-time Fourier transform to get D-shape synchrosqueezing transform. Okay, and here on the right-hand side, because of ground truth, I just superimpose the ground truth, and you can see it is almost recovered. Okay, you can also play with and demonstrate synchrosqueezing itself and so on, and see what you get. And here, what you may say is, oh, wow, it is not very clear, right? This is probably just because of the resolution of the screen. If now I increase the resolution, for example, I zoom in, then you can see it is kind of nice. Okay, you can even increase the contrast by playing with different weighting. For example, here, what you can do is here, you can, this is 0.995. That means I just take all time frequency representation, every pixels, and evaluate all the values at all the pixels, and then I just find the 99.5 percentile, and I truncate all the values greater than 99.5 percentile to 99.5 percentile. So if you want to enhance the contrast, you can change it, for example, to 99. So let's see what you will get. Okay, then, well, still not better. It's, well, slightly better. Well, whatever, but you know how to play with it. Okay, you can even make it 0.98 and so on, see what you get. Okay, now next. This is the clean signal above. Now let's plot all results of noisy signals. Of the noisy signal, and that's what you get. And you see the data is very noisy, but still you can get something reasonable after the shape, which in the shape short-time Fourier transform, it is not very it's not very good. Right here is well, but come on, this is minus 0.8 uh, uh, decibel, so it's maybe not too much to plan. It's already too very noisy, but you can get something already. And after you do the squeezing, you can see, hey, look, it is kind of much better here, right? So if I now zoom in, yeah, well, curve one, and this curve is actually, hey, there's still some information here, right? It's not totally empty, not totally junk. So if I superimpose the ground truth, as you can see, okay, it gives us a reasonably well estimate. Although here you can see some disturbance, but it's not too crazy. Okay, so which means it is okay. Yeah, we can kind of survive. And to save time, here I would just estimate amplitude modulation using ground truth. And you can just apply what we have done previously using synchrosqueezing, ridge extraction, and so on. For example, you can run synchrosqueezing, ridge extraction from the shape. Okay, and then once you get instantaneous frequency, you go back to synchrosqueezing to reconstruct the phase and amplitude modulation of each component. Okay, so all details are covered in the previous lecture, so I will just assume the ground truth so that we can do something. And next, when we run SAMD, we need some information. That is the harmonic order. So again, we just use a ground truth, you can estimate it. And for this kind of signal, the estimation is relatively easy. Okay, so that is what we have. Now we can run SAMD. I will explain SAMD in a bit, but let's run it first and see what we get. Okay, so this is the time. Let's see how much time it takes. It will take maybe 10 seconds or something. But when we wait, let's see what is SAMD. So the basic idea is very simple. You have a signal Y, which is modeled like what we discussed before. Okay, here, this is a time varying wave shape function model. And now you want to estimate or achieve the decomposition. Seriously, it is almost impossible because there are too many functional parameters to estimate. So we need to do some simplification, naive simplification. Otherwise, there's nothing we can do. It's too crazy. So we will slightly modify the approximation or the model in the following way. We say, hey, first, the amplitude modulation does not go crazy. It's just one. Okay, it does not depend on harmonics. Second, we will try to approximate the harmonics here. There's a lot of perturbation of the harmonics, multiples of the fundamental components harmonic phase. So what we do is we just do some simplification, saying that the higher order harmonics phase is simply the polynomial order of the fundamental component with some weight. That is a polynomial approximation. Okay, and then we estimate the global phase by putting some constant in front to do the estimation. So that is a basic approximation of one harmonic. Then we say, hey, although in general, the harmonic order or the number of harmonics can be infinite, but in practice, we will be satisfied by only finite harmonics. For example, in the simulation I generated, we only needed 8 harmonics. Okay, so this di is the harmonic order, which di, if we look at the code, okay, 10 seconds, we finish. It's not too bad. But let's take a look at results in a bit. So this is the harmonic order hat. So this is di. Okay, this is di. So this is d1, and this is d2 in the paper. Yeah, I think, yeah, remember this is follows the same notation in the paper. Okay, and then this k is the polynomial order that you call when you call, yeah, here, this harmonic order, I put 3 and so on. Anyways, now when you do the estimation, what you do is you simply say, hey, yi is roughly this guy. And then you approximate BI amplitude modulation function, phase, and so on by D-shape synchrosqueezing and synchro-squeezing. Okay, so again, we have discussed it, so that is what we'll skip. And then you just run some least square minimization. And this is because there are some parameters EI that is inside cosine. So this is in general a nonlinear regression problem. Okay, so this is set. And when you run it, you just you can check the code which I have shared with you and see how it is implemented. It's kind of very basic and simple. Finally, as I mentioned, how to estimate DI, you can just run trigonometric regression by linear regression ideas. That is, you fit everything by cosine. And this time, we assume, well, this is a very, very rough assumption, saying that the signal does not have crazy time-varying wave-shape functions, and so that you can simply use that assumption to further simplify the model so that you can apply some model selection ideas like AIC, BIC to decide DI, the harmonic mode by the fitting process. Okay, so that is the overall idea of the algorithm. Now let's see the result. Okay. So this is a result. Although, you see, hey, look, I use you cheat, right? How can you cheat? Because you use the ground truth. Yeah, I use the ground truth to simplify the the approximation. If you zoom in, you can see, well, even if I use the ground truth, it's not as perfect as we expect, right? This one is better. This one is not as good. And if you look at here, well, it's a bit, well, why is it so bad? This is not good. No, this is not good. Shit. I have no idea what's going on. Okay, but this one is good. Okay. Anyways, you know how to play with it, and you just need to fine tune it. So yeah, but overall it looks okay, right? But it just well, but come on, this is look the fitting is via the noisy data, so it's maybe not too much to play. Now suppose I say, how about if the harmonic order is wrong? Maybe I change it to 10. Then what will happen? We can play with it. Actually, harmonic order estimation, well, it's relatively easy, but usually not super stable. So, but no matter what, you can always play with it and we'll see what you get. Short answer is the algorithm itself is not super sensitive to the estimation of harmonic order. For example, this is the harmonic order assumption 10. You may get slight discrepancy, but that is not super bad. Not super bad. So if, for example, here, if you do a comparison They are slightly different, but not that different. And here, like, well, it's kind of, at least I would say, okay, not crazy. Okay, and you can say, okay, how about if the harmonic order is underestimated? For example, 5, what will happen? Then we can play with it again. You see, it is worse for sure because the order is the estimation is lower. Well, you see, there's a lot of details are missing for this one, and well, interesting. Even if lower order of low frequency component seems to be better, at least by my eyes. Okay, I don't know what's going on. There must be something wrong. Well, anyways, that is how you play with the code, and you can try to implement uh, this part as a homework. Okay, here I just use the ground truth. So what you can do is you can just apply what we discussed before about synchrosqueezing and ridge extraction and the reconstruction formula to get to the amplitude modulation, phase, and so on as a homework. Okay, and see what we get, what you get. That is very important. Okay, I think that is it for today.